Fucking hell, lads. Hot one today. Yeah, I'm going to be picking my own brains again. While I push for the burn. I was thinking about doing another Shrek episode, but I sort of went off the idea, I guess, when I discovered that in the third film he pursues sort of the family life. He has a load of kids, and yeah, I was just disappointed in the character development there. Shrek ended up being not the guy I thought he was. Had a load of disgusting children running around, and he let them live. So yeah, not big on that one. Can't bring myself to watch it now or even really talk about it. Maybe one day, but just left a bit of a sour taste in my mouth. So I had a load of exams last week for my university course, maths exams, and one of them was to do with complex analysis, which is, you know, sort of like, well, analysis for complex functions and sort of like integrals and limits, stuff in the complex plane. So I guess one theorem I wanted to talk about was the Cauchy Residue Theorem, because my lecturer was really raving about it, saying it's a fantastic thing, and like, to be fair to her, it's pretty useful, but I don't really get what it's all about. So yeah, the theorem states that if you've got a simple closed contour in the complex plane, so for example, if you had like a line in the complex plane that you sort of drew a shape with it and then it connected back to the beginning, that would be a closed contour. And a simple closed contour just means that it doesn't cross over itself at any point. So if you've got one of those and a function that's holomorphic, so that's a fancy word for differentiable. I guess I could go a bit into the definition of differentiability, but yeah, for complex functions, differentiability just means that the limit as the function, as the change in the function, which we assign some number, usually h. So the limit as h approaches 0 of the function at a point slightly above x, so x plus h minus the value of the function at x divided by h. If that limit exists, then the function's differentiable at that point, and that's what the derivative is equal to. So if you have a function that's differentiable or holomorphic everywhere in a domain, which is just an area of the complex plane, except at a few singularities of the function. I should probably explain what a singularity is. Singularities are points where the function may be sort of undefined or diverges. So, for example, if you had 1 over x, obviously if x was 0, you'd have 1 over 0, which isn't defined, and so you'd say 0 is a singularity of that function. So if you have a function that's holomorphic everywhere in a domain apart from at its singularities, so the domain would be defined in an area of the complex plane but not at the singularity. and the domain encloses this simple closed contour, so that the interior of the is it the union or the intersection? I think it's the union. It's the interior of the intersection, I believe, of the domain and the contour, and the contour is equal to the interior of the contour, not including the singularities of the function. So if you have sort of your domain, your contour, and your function all defined in that manner, then the integral of the function over that contour is equal to 2 pi I, where I is the imaginary constant, so the square root of -1. 2 pi I times the sum of the residues of the function at each singularity. So there could be multiple singularities of the function inside the contour. There could even be singularities of the function outside the contour and the domain, but you wouldn't actually need to worry about them. The only ones you need to worry about are the ones that are inside the contour. I should probably explain what a residue is. So the residue of a complex function at a singularity would be the coefficient of the x minus the singularity term when it's to the power of -1. So, for example, when you've got a function, you can express it in terms of a power series most of the time, certainly if it's holomorphic. So you've got power series. This could be a Taylor series, so one you might be familiar with is if you have the exponential function, and this is for a real function, not a complex one. You'd have e to the x is equal to the infinite sum of x from n equals 0 to infinity of x to the n over n factorial. But of course in that one there's no negative powers of x. So for complex functions we need to extend this notion of power series, and we end up with something called a Laurent series, I think is how it's pronounced, named after a French fellow probably. But that's like it's a similar thing, except it includes negative powers of x defined in an annulus, which is sort of like a donut shape. So you've got a point or a circle in the middle, and a circle on the outside, and the ring is the annulus. So if your function's defined in there, you've got a Laurent series for it. And so somewhere in that Laurent series you're going to have your complex variable take away your singularity to the power of -1, and then the coefficient of that term is the residue. And there's quite a few ways you can compute residues, but I guess the most general formula, let's see if I can remember this right. Well, it depends. There's a formula for if it's a simple pole, if the singularity is defined as a simple pole, which means that its power is -1 for the function, or it has order -1. If it's a simple pole, I think the formula for the residue is the limit as I should probably be using z, not x really. Let's say z from now on, because z typically denotes a complex variable. But the limit as z approaches the singularity of z minus the singularity times the function f of z. That's the residue for a simple pole. If you have a pole of order, well, anything from 2 onwards, which means that the power or the order is bigger than -1 for the power of the function, or the singularity of the function, then you have to use a formula which is, I believe, 1 over, for whatever the order is, it would be 1 over n, say the order's n, 1 over n minus 1 factorial times the limit as z approaches the singularity of z minus the singularity to the power of n times, oh actually no, I got that wrong, the nth derivative, what is the n minus 1th derivative? Yeah, the n minus 1th derivative of z minus the singularity to the n times f of z, I think. This is all just off the top of my head, so I might have made a few mistakes here and there, but that's how you would compute a residue. And so yeah, the theorem just states that instead of having to compute an integral for this function over the simple closed contour in the complex plane, you can just compute the residues of the singularities and add them up and times them by 2 pi I, and that's the answer. And I was just thinking, like, what's the deal with that? Yeah, just a bit strange, isn't it? I mean, Cauchy figured it out, so fair play to him. But just one of those things that you think, how does a human come up with that? And like, why? At what point in your life do you go like, oh, this integral is cool, but I can find a better way of doing it, so like, you know, check this out. I don't know, it's strange, isn't it? Something to think about. A bit of a boring one, to be honest, this one. But you know, they can't all be Shrek-tacular, you know, Shrek Bonanza things. Yeah, just sort of leaving the camera rolling for the sake of it now. I haven't got anything else to say. If you didn't know the Cauchy Residue Theorem before, hopefully you do now, and you can find some use for it. Maybe if you're going to study complex analysis next year, that'll be rooted in your brain. You're not going to forget about that now, are you? No siree. Yeah.